If we looked up at the night sky through a telescope, we would see millions and millions of stars of all different kinds of brightnesses and all different kinds of colors. We would see red stars, blue stars, white stars, yellow stars, and some of them would be very bright, some of them would be very dim. So we wonder if we could get any kind of an ordering to these stars that we see. Can we put them into any kind of a classification? Can we put them on any kind of a graph so that we have a lot of simplicity instead of the apparent disorder that we see if we simply look at them? Yes, the greatest order that we can achieve is that we put them on a diagram, a graph, which is called a Hertzsprung-Russell diagram. And for short, it's called an HR diagram. So let's investigate how well we can order the stars if we simply put them onto an HR diagram. So on the HR diagram, along our horizontal axis, we're going to track the temperature of the stars. And we're going to start at 3,000 degrees, and we're going to go up to 5,000 degrees, then we'll go to 10,000 degrees, 20,000 degrees, and then here we'll stop at 30,000 degrees. Now the surface temperature of our sun is 6,000 degrees, so it would be marked right in there. Now on the vertical axis, we're going to track the absolute magnitude of the star. That is the magnitude, the luminosity that we would measure if we went right up to the star and measured it nearby. Now we're going to count this in the number of times it is brighter or dimmer than our sun. We're going to take the standard amount of luminosity to be our sun, and we call that 1 solar luminosity. And we write it as 1 luminosity, and we put a little circle with a dot in it. Because when we put a little circle with a dot in it, it means that we're talking about the sun. So this is the amount of energy that our sun puts out in 1 second. It's called 1 solar luminosity. But we can have greater amounts of solar luminosities. We can go 10, 100, 1,000, and we can go all the way up to 10 to the 6 as well. And we can have lesser ones. We can have 1/10 of a solar luminosity, or 1/100th, or 1/1000th, or 1/10,000th of a solar luminosity. So these are the two parameters that we will use to classify all of our stars. What is the surface temperature of the star, and what is the absolute luminosity? Now the absolute luminosity is plotted in the usual way of a graph, that is the highest numbers as you go upwards. But this graph, in historical reasons, because of the way it was done first, and you might say that it makes a little bit more sense when you look at the final product anyway, is that the temperature increases as you come into the left. Ordinarily, on the horizontal axis, the value would increase as you went out to the right. So in this one, the first thing to note is that the temperature increases as you come into the left. Now let's find the position of our sun on this star. Well, the graph. Well, it is 1 solar luminosity, and it is 6,000 degrees. So we put an X right there for our sun. Now, if we measured the luminosity and the temperature, which we can do because of the maximum wavelength that it emits, of a large number of other stars, we would find that 95% of all of the stars that we look at fall into a band. 5% of the stars fall outside of this band, but 5% of the stars that we look at fall in, 95% of the stars that we look at fall into this band. That is the temperature that they have on the surface and the luminosity with which they shine would cause them to produce a dot that's right along this band. So we call this band the main sequence. Since 95% of all stars fall on it, it is the main place that stars appear. And it has a different mass as you go from lower to high. Right here, our sun, of course, is 1 solar mass. And we designate that as a 1 with an M, and then the usual circle with a dot in it to indicate that we're talking about a property of our sun. And as we went up, then these stars would have more mass. Now, because they have more mass, it means that they have more gravity, and it means that their core is more dense. And when the core is more dense, it achieves a higher temperature. When it achieves a higher temperature, there's more nuclear reactions. When there's more nuclear reactions, the star is brighter. So as you increase the star, then obviously it gets brighter, and because the core temperature is hotter, then when the temperature works its way out to the surface temperature is also hotter. So these main sequence stars go up to 10 solar masses, and they also go up to 20 solar masses. And they can also go very, very small. They can go all the way down to 0.5 solar masses, if you will, and maybe even a little bit less. Let's just see how low we can go. We can go to 0.1 solar mass all the way down at the end. So we have 0.1 solar mass, or here we have 0.5 solar mass. Now what about those other 5% of the stars? In some way, they are the more intriguing. If we go above 20 solar masses, then this star no longer has the same physics as the stars that are in the main sequence. It has a completely different physics. And what happens is that the physics that it does have causes it to expand and to expand and to expand and to achieve a gigantic radius. And because it has such a radius, as we learned in our luminosity law, that means that even though the temperature hasn't changed, the surface area has, and therefore it's going to have a huge luminosity. So we would expect these stars that are larger, say 30 solar masses, and obeying different physics, to have an incredibly high luminosity because of the fact that they are very, very large and they have a very high surface temperature. So up here in this region is what we have is called the blue giants. They are blue in color because they are a very large star, they have a very high core temperature, and they generate a lot of nuclear reactions, and that temperature reaches the surface, so they're a very hot star in the surface, and they expand because of their internal pressure, so they're a very large star, so they generate absolutely huge amounts of energy. We have some other giant stars that are just as large as these. However, their surface temperature, because of a different physics inside, which we'll look at in a later chapter, their surface temperature is a lot cooler. So even though they have the same surface radius, meaning they're going to emit a lot of luminosity, because their surface temperature is lower, their overall luminosity will not be as large. And these are what we call the red giants. An interesting fact that we will see in a later chapter is that each star that is a red giant, some millions of years ago, it was on the main sequence. And then its physics changed. And just as in people, when they go through middle life and then go into later life, their appearance changes because of the physics inside. The physics inside the main sequence star changes, and because of the changed physics, then the star expands, and it becomes what's known as a red giant. And just as a little bit of a side, our own star, in 5 million years, is going to go through the same sequence. It will also expand, and it will become as large as the orbit of the Earth, and we will be inside of it. So these red giants are main sequence stars that went that direction in later life. Now there are even giant stars that are larger than the red giant stars, and those are called the red supergiant stars up in that region. But a very interesting later step comes in these objects, which is that the red giant star, after it burns out all of its fuel, it has nothing left to resist the crushing force of gravity. It can't push back out anymore. So gravity starts to squeeze it together after all its fuel is gone. And therefore, what happens is its radius gets very much smaller and smaller and smaller. And as its radius gets smaller, then it shrinks down to a very small size, and it doesn't emit very much luminosity. So it will end up down here in this region of very low luminosity. And the color that it emits is going to be pure white. So here's where we have the white dwarfs. The other dwarfs that we have are the ones that are way down here on this end of the main sequence. They have very low luminosity because they have very small mass and very low size, so they don't put out much total luminosity, and because they have small mass, they can't generate very much temperature in their core, so therefore they have a red color as well. Their surface color is also lower. So this is the main classification that we put out here on the Hertzsprung-Russell diagram. We have the main sequence stars, we have the white dwarfs, and we have the blue giants, the red giants, and the red supergiants. Now, if we look at the mass-luminosity relationship, which we can remind ourselves it's equal to L equals sigma t to the fourth times 4 pi r squared, which is the surface area. Now, if we hold the radius constant, and we want to say, how does the luminosity go with temperature as we hold the radius constant, then what we can draw on this graph are lines of constant radius, which will turn out to be very interesting. Now, if we draw a line right through the sun, then this will be 1 solar radius. 1 solar radius. And if we go up a little higher, then all the stars that are on this line will have 10 solar radii. And all the stars that are in this line will have 100 solar radii. And all the stars in the supergiant region will have 1,000 solar radii. Meaning that a red supergiant has a radius that is 1,000 times as large as our sun. And we can go down lower as well, and we can get a 0.1 solar radius, and we can go lower than that and come all the way down to a 0.01 solar radius. So this Hertzsprung-Russell diagram is a compactivization of lots and lots of different kinds of data. It tells you the surface temperature of the star, it tells you the luminosity of the star, it tells you something about the internal structure of the star. And that is very, very neater than looking at lots of stars and not knowing how to classify them at all. They all fall into place, 4 or 5 very simple places when you use the Hertzsprung-Russell diagram.